Hello everyone. This is Dilip Chakravarti, Assistant Professor in Cybersecurity Department in Institute of Aeronautical Engineering. Today we are going to discuss about binary search trees. So far we discussed about trees and binary trees. So let's see about what are binary search trees. We all know binary trees means which can take maximum of two children, maybe zero or one or two child. Okay, we call it as binary trees. But there are some drawbacks in binary trees. So if you are continuously adding, inserting elements, we can insert the element as a left child or right child. For searching that element, it takes a lot of time to search. We are not following any procedure there. Okay, so in binary search tree, we are using some conditions, some mechanisms such that we can search our data quickly. Okay, we can get our data quickly. So uh, So binary search tree is a binary tree in which every node contains only smaller values in left subtree. Okay, if you take a root node, all the elements that are less than that root node will be placed in the left subtree, and all the elements which are greater than the root node are placed on the right subtree. Okay, so this is a formula, or this is the mechanism we are following binary search trees. To enhance the performance of binary trees, we use a special type of binary tree known as binary search tree. So binary search tree mainly focus on search operation in the binary tree. Okay, so here we mainly focus on search operation. Every binary search tree is a binary tree. Okay, we can say every binary search is a binary tree, but every binary tree need not be a binary search tree. Okay, it is not compulsory that every binary tree is a binary search tree, but every binary search tree is definitely a binary. Okay, so if you observe this, in a binary search tree, all the nodes in the left subtree of any node contain smaller values, and all the nodes in the right subtree of any node contain larger values, as shown in the following figure. If you observe, k is my root node, and mm, all the elements that are less than k, so they are placed as the left subtree, contains only smaller values. If you observe here, it contains only smaller values which are less than k. And on the right side part, it contains all the values which are greater than k. Okay, it contains only larger values of k. Okay, so it looks like that. Let's see with a simple binary search tree example. The following tree is a binary search tree. In this tree, left subtree of every node, if you observe any node in the left subtree, it is always less than the root node. Okay, for this one also, if you observe here 10, so all the elements that are left to this are less than 10. Okay, all the elements that are right to this are greater than 10. Okay, if you consider any node, okay, so any subtree or any total tree, all the left side elements are less than the root node, and right side elements are greater than the root node. Okay, so observe here 36, which is greater than 25. So here 30, 28, which are less than 36. Okay, so we'll be placing like that. Let's see how we are going to construct a binary search tree by inserting the following sequence of numbers. Okay, I need to construct a binary search tree. So given these are the elements, okay. So first I'll consider, I will take 10. As nothing is there in my trees, first I'll make 10 as my root. Okay. Now I got 12. What I need to do, I need to insert. Okay, as 12 is greater than 10, I'll be placing it as the right shape. Okay, then insert 5. As 5 is less than 10, I'll be placing it as a left shape. Okay, So in this way, I'm going to insert. Then for inserting 4, will be first checking with my root node 10. As 4 is less than 10, I'll move to the left. So already 5 is there. I'm checking with 5 again. As 4 is less than 5, I'm placing it as left child to 5. Okay. Similarly, now insert 20. So first I'll come here, I'll check with my 10. So as 20 is greater, I'll move to the right side. So here 12 is there. So as 12 is less than 20, I'm placing it as right child to my 12. Okay. So 20 is placed as right child to 12. So insert 8. Again, I'm comparing with this element and this element, and I'm inserting at right side of 5. Okay. Insert 7. First, I'll be checking with my first node. 7 is less than 10. I'll be moving to left side. So 5. So 5 is less than 7. So then I have to move to the right side. So here I'm comparing 7 with 8. As 7 is less than, I am placing it as left child. Okay. So then insert 15. So I'll be checking with my root node 10, and 15 is greater than 10, I'll be moving to the right side. 15 is greater than 12, I'll be moving to the right side. 20 is which is less than 15. 20 is greater than 15. Okay, that's why I need to place 15 as left child to my 20. Okay, so finally I need to insert 13. So I'm inserting it. I'm checking with each and every element. Okay, so as 13 is less than 15, I'm inserting as a left child. Okay, so if you observe in any tree, in all these notations, always left subtree is less than the root node, and right subtree is greater than the root node. Okay, so similarly for constructing this binary search tree, see this. So starting with 43, I made it as root node. Then 10 is added as the left child. 79 is added as the right child, as it is greater than the root node. Okay, then 90. So I am checking with my first node, root node. As 90 is greater than 43, I moved 7 to this position. As 90 is greater than 79, again I move to this position and I am inserting here. Okay, so then coming to 12, for inserting 12, so I'll be checking with my first element. As 12 is less than 43, I'll be going to the left side. And I'm checking with 10, as 10 is less than 12. I need to place 12 as the right child to my 10. Okay, similarly for inserting my 54, for first, I'll check with my first node 43, as 54 is greater than, I'll be moving to the right side 79. I observe that 79 is greater than 54, then I place it as a left subtree. Okay. So similarly, I'm going to add 11. Okay. So I'll be checking with each and every node. If it is greater than, I'll be moving to the right subtree, and if it is less than, I'll be moving to my left subtree. Okay. Okay, so here also I'm inserting element 11. First, I compared with 43. As 11 is less than 43, I went to the left side 10. So I checked it at 10, and I compared with 10 and 11. As the 11 is greater than 10, I moved to right side, and I compared with 12. As 11 is less than 12, I'm just adding it as a left child to my 12. Okay. So finally, for adding 50, first I'll check with 43. Then I move to, as 50 is greater than 43, I move to the right side. Then mm, at 79, you will be comparing. As 50 is less than 79, I'll move to the left side. And again, I'm comparing 50 with 54. 50 is less than 54, I'm making it as a left child to 54. Okay. In this way, I'm inserting all the elements. So there are some properties of binary search trees. Okay, in order to say this tree as binary search tree, there are some properties. What are those properties? Binary search tree is a node-based binary tree data structure which has the following properties. The left subtree of a node contains only nodes with keys lesser than the nodes keys. Okay, so on the left side, you'll have only the keys that are less than the root node. Okay, similarly, on the right side, uh, you'll find only keys greater than the root node. Okay, and the left and right subtree each must also be a binary subtree. The left subtree and again right subtree. See, both the left and right subtrees are again those are those should be binary subtrees. Okay, so then duplicate node keys are not allowed. It should not contain no, same keys, same element. Okay, duplicate nodes keys are not allowed. And in order traversal of BST visits the keys in increasing order. If you are writing an in order traversal of BST, you will get an increasing order. Okay. What are the advantages of binary searching? Searching becomes very efficient in binary search tree. Okay, so if you are using binary search tree, it is easy to find the element. If the element is greater than, I'll be moving to the right subtree. If the element is less than, I'll be moving to the left subtree. Okay, so I'm not checking a whole tree. Okay, this one greater advantage. The binary search tree is considered as efficient data structure. Compares to arrays and linked lists in searching process. It removes half subtree of every step. Okay, so as I already told you, in every step, if the element is greater than, I'll be moving to the right subtree. I'm not checking in the left subtree. Okay, suppose if the element is less than, I'll be moving to the left subtree. I'm not going into the right subtree. That means every time a half subtree is removed at every step. Okay, so this is also one advantage. Searching for an element in binary search tree takes order of log to n time. Okay, in worst case, the time it takes to search an element is order of n. Okay, so then it also speed up the insertion and deletion operation as compared to array and linked list. Okay, if you are using binary search tree, we can easily insert an element at correct position. Similarly, we can easily delete the element from a tree binary search tree. The following operations are performed on binary search trees. Binary search. What are the operations? If you observe search operation, insertion operation, deletion operation. Okay, so we can search an element, we can insert an element, we can delete an element from a binary search tree. Okay. The following operations are performed already as we have seen searching in binary search tree. BST is nothing but binary search tree, finding the location of some specified element in binary search tree. Where you found the element, you are considering you are finding the location. Okay, and then you are checking. Uh, you are trying to insert a new element into the binary search tree. Okay, it is nothing but adding a new element in a binary search tree. So you can delete an element in a binary search tree. So search operation is performed to search. Okay, let's see one by one: searching, insertion, and deletion. Searching in binary search trees, search operation is performed to search a particular element in a binary search tree. Whenever an element is searched, start searching from the root node. Okay, then if the data is less than the key value, whatever you are searching, if it is less than the no root node, you will be moving to the left subtree. Okay, otherwise search will be proceeding to the right side. Okay, so we'll see the algorithm for this binary search tree. So read the search element from the user. Okay, you are going to find what element to search. You are going to take that input, comparing the search element with the value of root node. This is the second step. If both are matched, then we are displaying the node is found, the element is found. If both are not matched, then check whether such element is smaller or larger. Okay, so I'm checking whether it is smaller or larger. If such element is smaller, so then I move to the left subtree. My search proceeds to the left subtree. If it is larger, then the search procedure continues in the right subtree. Okay, we are going to repeat the same procedure until I found the element. If we reach to the node having the value equals to the search value, then display element is found, and we are going to close that. Otherwise, if you are not seeing, if you don't find that element, if you reach to the leaf node, and if it is also not matched, the search element, then displays element is not found. Okay, so in this way, I'll be proceeding my search process. So observe here, element to be searched 10. I'm going to search 10. First, I'll be comparing with my root node 12. So as 10 is less than 12, I'll be moving to left tree. Okay. So here again I'm checking. So as 10 is greater than 7, I'll be moving to my right side. So here again I'm checking. As 10 is greater than 9, I'll be moving to my right side. So finally, I got my 10. Okay. My search is successful. Okay. Similarly, for element 45, we need to search 45. So I am searching. So first, I am comparing with my root node. As 45 is greater than 25, I'll be moving to right side. Here I found 50. 45 is less than 50. I'll move to the left subtree. So here 35. 35 is less than 45. I'll move to the right subtree. Okay. Here 44, which is a leaf node. Okay, so already we reached to the leaf node, and this leaf node is not my searching element. This is not 45. So hence I conclude that this is my search is not successful. It is unsuccessful. Okay, element is not there. Okay, element is not found. We can say that one. Okay. And insertion in binary search tree. How I am going to insert an element in a binary search tree? Here, some few steps, the same steps I'll be checking with my root where I need to insert. Okay, so I'm considering. I'm comparing with my root element. So if it is larger. Then move to its right child. If it is smaller, then move to its left child. Okay, so we'll be doing this procedure until I reach to the position. Okay, so there after reaching to the position, after reaching the leaf node, insert the new node as a left child if the new node is smaller, or equal if the node is greater than that element, then we will be inserting it as the right chain. Okay, so we'll see with an example. You get a clear idea here where I need to insert 4. Where I need to insert, first I'll go to my root node 8. I'm comparing with my 8. As 4 is less than 8, then I'll be moving to left. That means I am going to 3. Again, I'm checking there. As 3 is less than 4, I'll be moving to right to the 6. Okay, so then again I'm checking here. As 4 is less than 6, I'll be making my 4 as a left child to my 6. Okay, so in this way I'm inserting my element into binary search tree. Okay, consider the following example where if 40 is to be inserted. Okay, I am trying to insert 40. So first I'll go to the first element root node. As 40 is less than 100, I'll move to the left subtree. So 20 I found. As 20 is less than 40, I'll move to the right subtree. So as again I'm checking 30 with 40. As 40 is greater than 30, I'm inserting it as right child to my 30. Okay, so finally deletion operation in binary search. How I'm going to delete an element in binary search? Here there are three cases in deleting a node. Okay, so here we are following some procedure now for that. before deleting, we need to see some cases. So what are those cases? Means, am I deleting a leaf node? Am I deleting a node with one child? Am I deleting a node with two child? Okay, we'll see all those things one by one, starting with the first node, deleting a leaf node. If I'm trying to delete a leaf node which is not having children, no children, just I can remove that element. Okay, no need of worrying about anything. So I can just remove it from my tree. Okay, find the node to be deleted using search operation. Using search operation, I'm going to find which one I'm going to delete, and I just simply delete the node using free function. Okay, observe this example here. 19. In this case, 19 is the leaf node I need to delete. As there are no children, I'll simply delete 19, and my tree becomes like this. Okay, so this is my first case. Second case, deleting a node with one child. Suppose if there is one child to my deleted node, whatever I am trying to delete. So at that time, remove that node, and the child should be placed. You should give the link to child and parent. Okay, so you simply delete that node and give the link to parent and its children. So find the node to be deleted. If you see the algorithm steps, find the node to be deleted using search operation. If it has only one child, then create a link between its parent node and child node. Okay, delete the node using free function and terminate the function. Okay, we'll see with an example. See, observe here, 9 is having one child 10. Okay, so if I'm trying to delete 9, I just simply delete 9 and I will put a link between 7 and 10. Okay, now my tree becomes like this. Okay, so simply I'm deleting the 9. Okay, so and finally, a third case, deleting a node with two children. Suppose if there are two children for a deleted node, then I need to do any one method. There are two methods I can follow. First thing is, if I see, observe the steps, visit to the right subtree of the deleting node. I will go to the right subtree, plug the least value in the right subtree. Okay, so you need to pick the least value in the right subtree, and I'll be placing that element at the deleted element position. Okay, replace the deleting element with its in order successor. Okay, this is one method. Okay, where I can replace it by the least value in the right subtree. In the second method, I can place it with greatest value, largest value in the left subtree. Okay, so I can implement that procedure also in the second method. So we'll see example for this. Consider this example where I need to delete 15 as 15 is having two children, 10 and 17. So before deleting that 15, I can implement any one of the method. As I already told you, if you are considering left subtree, then you have to take the greatest element in the left subtree. Or otherwise, if you are considering right subtree, you have to take the least element in the left subtree. Sorry, right subtree. Okay. So here in this procedure, I have taken least element from the right subtree. 16 will come here, so it will be done like this. Okay, in this way deletion operation will occurs. I hope it is clear. Thank you.